So hello everybody, it's 2 o'clock and we're delighted to welcome you to today's webinar, which is titled Methane, a One Health Perspective. We would like to welcome the audience. Thank you for joining us. And of course, we'd also like to welcome our speakers, Professor the Lord Trees, Professor Jonathan Stern, and Assistant Professor Jonathan Bunacore, along with Dr. Lisa Crump, who is Deputy Editor of CABI's One Health Knowledge Bank. I'm Georgina Grell. I'm publisher of CABI's One Health Knowledge Bank and Animal Health Portfolio. I look after the Knowledge Bank with my colleague Frida. The One Health Knowledge Bank is part of CABI's integrated One Health resources, which also includes One Health cases, which provides real-world examples of One Health projects, and CABI's One Health Journal, which is a truly transdisciplinary open access publication emphasizing the interconnectedness of humans, animals, plants, ecosystems, and their shared environment. So I'd like to introduce you to Frida, my colleague.
Hi. Thank you all for joining. It's wonderful to have you connected to this webinar. So those who are unfamiliar with CABI, we're a not-for-profit organization and we focus on international development all around the world. We're supported by a publishing division, which we're part of, as you can see, One Health Knowledge Bank and other products that I work on, because I'm the associate publisher for the public health portfolio. So I also work on a couple other products as well. So we also have an amazing scientific research base, which if you ever come to CABI, you'll see the amazing things that are done as well in that end. So for over 100 years, CABI has been applying scientific expertise to solve problems in agriculture and the environment. And all the profits from our publishing arm support all this international development work that improves lives worldwide. And it's really great to see the impact of a lot of these projects. And you can actually explore these on our cabi.org page if you ever want to take a look. Many of these projects align with several sustainable development goals. And our publishing department offers a lot more than One Health. We have several collections and databases that you can explore as well. Today's webinar looks into the role that livestock and fossil fuels play in methane production and the role that methane plays in climate change, public health, agriculture, ecosystem, sustainability, and looks at the relationship between these for a One Health approach. And I'm happy to hand over to Dr. Lisa Crump, who you mentioned before, works on One Health cases as well as other things as well. So she's done really well before, and we look forward to continue to moderate. Thank you.
Thanks, Frida. So hello, everyone, and a very warm welcome from Switzerland. As mentioned, I'm Lisa Crump. I am by training a veterinary epidemiologist, working for the last 15 years at the Swiss Tropical and Public Health Institute in Basel and now Allschwil, Switzerland. Most of my work as a research scientist is based in Africa and Asia, and I'm working to implement integrated health approaches, primarily in resource-poor communities, very often in collaboration with smallholder farmers, mobile pastoralists, and community decision makers to increase access to healthcare. And as Georgina mentioned today, I'm here in my role as Deputy Editor for CABI One Health. I do hope that you will take a look at the CABI One Health suite to see the different products, the One Health Journal, the One Health cases, and the Knowledge Bank. Through the Knowledge Bank in particular, we're aiming to bring together diverse types of knowledge, including that from academic and non-academic communities, and highlighting the transdisciplinary work that goes on in order to generate those kinds of knowledge. So I'm sure that we'll come away today with a deeper understanding, probably also some new and unanswered questions, because I find that's always the way it is in the sphere of research and policy and education. So without any further delay, I'm delighted to start introducing our three distinguished panelists who will share from their respective work, their perspective on the complex topic of methane. So first of all, we're going to hear from Professor the Lord Trees, FRCVA, FMedSci, Honorable FRSE. So he is a fellow veterinarian, but more recently a crossbench peer since 2012 and a member of the House of Lords Environment and Climate Change Select Committee. Lord Trees will take us into the topic of methane with livestock in our focus. So I'd like to turn the microphone over to you now, Lord Trees. Thank you very much.
Thank you very much, Lisa. This is a complex subject, and I've only got 10 minutes, so it's going to be a bit of a race and a bit simplified. I'd just like to acknowledge the terrific help of my researcher, Fiona, who's on my left off screen, who's also a vet in preparing this. I want to focus on two greenhouse gases, really, and the net zero and the impact of livestock, CO2 and methane. Now, in 2019, the UK committed to reducing net emissions of greenhouse gases to zero by 2050. Now, net zero is otherwise called territorial emissions, and it's all the greenhouse gas emissions or removals from goods and services produced in the UK. What it does not include are air travel and shipping, burning biomass, including wood chip at Drax and so on, and particularly important, all the imported goods and services we use. They are included in the metric called consumption emissions or carbon footprint, if we can get rid of that. And that distinction is hugely important. The next graph, if we can have the next slide, shows the distinction between these two things. Sorry, the graph beforehand, thank you. On the bottom line, the green line shows the net zero progress we've made, the territorial emissions. And there's been about a 50% reduction there, which is quite good progress, with a target of 2050. Above, though, are the consumption-based emissions, which is our total carbon footprint. And there the progress is a lot less, at 20%. So you can see that the easy way of getting to net zero is to import everything, but that would be economic suicide, and it wouldn't do the climate change one jot of good. If we move to the next slide, please. The two gases we're focusing on, methane and CO2, differ in potency and persistence in the atmosphere. So methane is has a high potential for warming compared to CO2, but is present in the atmosphere for far shorter, about 12 years, whereas CO2 persists in the atmosphere for hundreds of years, even thousands. The graph on the right shows the difference, the warming response to a single pulse of methane, the blue line, and you can see a rapid warming response, but then which quickly cools, compared to the red line, which is the response to a single pulse of CO2, but which persists in the atmosphere, and the warming response persists too. If we move to the next slide, and this graphic and the previous one were generated by climate experts at the Oxford Martin School in Oxford University. If we look at the middle panel, constant emissions, we see the difference between CO2 and methane. Constant emissions of CO2 mean that the concentrations in the atmosphere accumulate, thus warming continues progressively and indefinitely. Whereas with methane, the warming reaches an equilibrium as the methane concentration reaches an equilibrium as decay equals emission. And in terms of falling emissions, we see that we get a rapid response in terms of reduced warming in response to methane emissions mitigation, whereas any emissions of CO2, even falling emissions, continue to accumulate in the atmosphere and increase warming. If we look at the next slide, this shows warming metrics which are applied by climate scientists and in policy making. The main metric used is global warming potential 100. It's internationally recognized, but it has major limitations when it comes to incorporating methane because of the very short life of methane in the atmosphere, and it's summed up there. And it fails to account for the cooling effects when methane emissions are reduced. So another metric has been devised called GWP star, which better accounts for the climatic warming associated with methane's short lifetime. And if we apply those two metrics with regard to livestock, GWP star gives a total warming value per unit of livestock product substantially lower than that GWP 100 gives. The next slide shows UK's anthropogenic methane emissions and their changes up to 220 from 1990. We've had a big reduction in the blue line for methane from waste. We've had a big reduction in the green line from fossil fuel extraction and burning. The red line shows what's happened with regard to agricultural methane emissions, and they've come down a little bit, but not very much. So that if we look now on the next slide, UK's agricultural emissions of methane are 50% from livestock, which is now the major source of methane emissions in the UK. Globally, livestock are responsible for a slightly less percentage, 32%. That's partly as a result of rice paddies, for example, which are a source of 8% of global methane emissions. Next slide, please. This just makes the point that cattle, of course, ruminants, but particularly cattle, are the main source of livestock emissions. 85% of those emissions are from enteric fermentation, mainly eructated, i.e. belched, but about 15% are from manure and slurry. Now, the next slide shows the differences, the range of emission intensities across over 300 UK beef farms. And it's to make the point that there is a huge variability, even in one country like the UK, even with beef, across different farms. The other take-home message from this histogram is the distribution. There's about a 5-fold difference between the best performing farms, the ones with the lowest carbon footprint on the left of the diagram, compared to the worst performing farms on the right. So there's huge potential for us to improve the performance in terms of emission intensities, that is the amount of greenhouse gas per unit of productivity. And that's a key measure that we need to be looking at in terms of agriculture. The next slide gives some comparisons between geographical regions, global, Western Europe and UK, bearing in mind there is huge variability here between even farms. But if you look at the right-hand column, the methane produced per kilogram of protein, the UK cattle conventional rearing at 1.67 is substantially better than the global average and even better than Western Europeans' average. So our productivity is pretty good. The next slide sums up the factors which affect methane output. Basically genetics, which affects both individual and breed variation, health, both morbidity and mortality are important, and diet. These can be summed up in the next slide, really, which is an illustration of how milk productivity from each cow, next slide, please, varies with regard to emission intensity. So to the right, the lower range, these are individual cow records. The highest producing cows are on the right-hand side, the lowest producing are in the left. But you can see that the emission intensity is much better in the higher producing animals. So improving productivity reduces emissions per kilogram of output. So if we look at the next slide, this sums up methane mitigation strategies, many of which are to improve productivity. So we can do it with breeding, genetics, improving health, dietary management, some specific feed additives, one's being marketed now in Britain, and potentially in the longer term vaccination against methanogenic archaea, the microorganisms which produce methane. These are not mutually exclusive, but it's important if we adopt any of these mitigation methods, we don't negatively affect other variables. And there are other methods available, different, but there are a number of methods available to reduce methane emissions from manure and slurry. Next slide, please. Of course, we have to set these measures in the context of the value of livestock to humans worldwide. And this is considerable, particularly in indigenous communities, nomadic pastoralists, but all of us have a dependence on food security and supply, to which livestock make a big contribution. They contribute to habitat restoration, biodiversity, and the carbon sequestration in grasslands and soil health. I would just point out some of the criticisms of ruminants, such as deforestation to create grazing and water use, do not really apply to temperate climate areas like the UK. So in conclusion, if we look at summary in the next slide, reducing methane is an important target because it's a quick win to deal then with CO2, which is ultimately what we need to reduce to permanently stop climate warming. Ruminants are significant in global methane emissions, but their role is complex and variable. And unlike some sources like waste, they do provide a lot of human benefits. There is huge scope to reduce ruminants' methane emissions. And if we look at the next slide, in the UK, methane emissions from ruminants are stable or reducing. We're not contributing to global warming per productivity unit. And we are better than the global averages. Last point I would make there is the global demand for meat and dairy is going to rise, and there is an argument that the UK should produce meat and dairy for the world. So in conclusion, the UK, in conclusion, in the next slide, please. Here in the UK, we must guard against destroying our indigenous livestock industry with the consequence of inevitably importing more meat and dairy produced with poorer environmental efficiency. And remember, that doesn't count towards net zero, and lower standards of animal welfare. Just final slide, please, acknowledges the support of the Veterinary Policy Research Foundation, and you can find more information on that website shown there. Thank you very much.
Thank you, Lord Trees, for the interesting presentation. We do have a couple of questions coming into the chat, so I'll go ahead and start with those then. From Wendy Hall, she asks, do any productivity measures include protein and fat? Her question is, if they don't, then maybe you're looking at increased water content. And this question is relative to methane production amongst dairy cattle.
The short answer is yes. I mean, it is stated actually on some of those figures, but I appreciate very small fonts on some cases. But you will be able to look that up, particularly the case with milk. But it's either dry matter and protein or fats as well. They are included in those estimates. Yes.
Yeah, and I think I can say that we will be able to share the presentations on the Knowledge Hub afterwards. Am I correct in that statement, Georgina? It's depending on whether we have the permission from our presenters, but I think we will be able to share those.
Yes, people will be able to watch the webinar again, and I'm sure with permission we can share the slides.
Yeah. Okay, I'm going to go ahead to the next question, which comes from Evan Griffith. How do methane emissions differ between intensive production systems like those in the UK and more extensive or pastoral systems where high inputs aren't possible? There's a related question, but let's start with that.
Yeah, it's a good question. There isn't over much data on this actually, but there's an American study which showed that actually extensive grass-based systems were slightly worse per unit of productivity. However, a lot of these analyses do not take full account of the carbon costs of all the inputs, and intensive systems required in general far more inputs in terms of fertilizers to produce the fodder itself, the transport of fodder, the waste dissemination and other inputs. So that's a debate which will continue. But I think what is important to use the resources we have in a temperate climate like the UK, where we have a lot of grass-based systems. You've seen the overall average emission intensity per unit of productivity, and it's world beating.
Yeah. I have quite a few more questions. We're at time, so I'm just going to go with one more, and then we'll circle back at the end. But while our next presenter is speaking, if you and your assistant want to type any answers into the Q&A, Lord Trees, you're very welcome to answer them then. I'll go with one more question verbally. This comes from Alex Caron. A production system can be seen as units produced per area. And so in extensive production systems, like pastoralism, livestock emit CH4, but in the areas where they graze, like the savanna, the stocks are CO2. And so do we have a good measure of production system emissions? In other words, the balance between the unit emissions and the habitat capture? I think it's an interesting question.
Yeah, it's a good question, and I can't give you an immediate answer. There's no question. A lot, extensive livestock systems use a lot of land, and we're very acutely aware of that in the UK. On the other hand, much of it is land that is not suitable for many other uses. And that applies in the UK to hill ground and rough ground. It applies in many savanna systems, which are natural extensive grassland systems, like the pampas and savannas in Africa. So they exist, and they do have a lot of benefit, those grassland systems in terms of carbon sequestration and so on.
Yeah, thank you very much. We could go on and on, but I'm going to go ahead and move on to our second speaker, Professor Jonathan Stern, who is a distinguished research fellow at the Oxford Institute for Energy Studies, where he founded the gas research program in 2003, and in 2011 became its chairman and a senior research fellow. In October 2016, he became a distinguished fellow, and he's an honorary professor at the Center for Energy, Petroleum, and Mineral Law and Policy, University of Dundee, as well as a distinguished research fellow at the Institute of Energy Economics in Tokyo, Japan. For the past 5 years, his research has focused primarily on methane emissions from the oil and gas sector, with many resulting publications that I will allow you all to look up later. Professor Stern, the floor is yours.
Thank you very much, Lisa, and hello everybody, and pleasure to be with you. As Lisa said, I've been working on methane from fossil fuels for the past 5 years, which in this context does not make me much more than a beginner, I will tell you, and I will try and explain why that is. If we could have the next slide, please. So this is just a summary slide. So anthropogenic methane emissions, around 390 million tonnes in 2023, of which 1/3 energy. In many countries, as Lord Trees has shown you, agriculture and waste are more important sources of methane than energy. But the reason that everybody focuses on energy is that basically oil and gas emissions, and to some extent coal, are the easiest to address and minimize, partly because if you take the top 200 companies, you've actually accounted for a lot of those emissions worldwide. They're also among the lowest cost ways of reducing overall greenhouse gas emissions, which can have the most immediate impact on warming. Depending on the price of oil and gas at any one time, roughly 40% of methane emissions can be eliminated at no net cost, which raises the question why we haven't had more success in the last several years. The next part of the slide shows you the various initiatives that have been opened up, many of them in the last few years, which I could elaborate on if people are more interested later on. But let's hurry on to the next slide. So this is about global methane emissions from energy. I mentioned the concentration of emissions. So 70% come from the 10 countries that you can see at the bottom of the slide, which really gives you an idea of if you can do something major in those countries, you can really make a big impact. Perhaps a little bit counterintuitive, given that natural gas is methane, a little bit counterintuitive is that actually emissions from natural gas are less than either coal or oil. Coal is really, really difficult because of the problems that you have with coal mines that may continue to emit methane even once they've been closed and are no longer working. But you'll see that there's really the biggest source is oil. And this really stems from the fact that most recently we've discovered that flaring, that is burning of gas from mainly oil fields, is a much bigger component than we thought, which you'll see in the next slide. So the three main sources of emissions are fugitive, sometimes called leakage, vented, which nobody really knows about, but which is the most important source, and flared. Just dwelling on this for a couple of minutes, essentially venting, which is essentially allowing gas to escape as pure methane, is extremely important, particularly for oil fields. And it's extremely important because we don't it's very difficult to measure and capture exactly how much is escaping, and because it is generally held to be a safety issue. In other words, because the methane is combustible, it is often vented in order to prevent explosions. If we then move towards the next one, it's fugitive, that is leakage, which is usually unintended leakage from pipes. And finally, flares. Now, I mentioned that flares have been recently upgraded, but they are still, of the three, the least important, although the most visible, because, of course, every time you get a snapshot or a video on the television of a field when you can see the gas being flared off, you get the impression that this is the most important escape of greenhouse gas emissions. It's very important and it's relatively easy to deal with, but it is not the most important. Incidentally, one of the strange things about collecting these emissions, where you can see the zeros opposite onshore and offshore gas under flared, that is probably not correct, but the problem is actually collecting that data. So let's move on to one of the most important things that's happened in the last year, which is the introduction of the EU methane regulation. Now, this is terribly important because the EU became aware that because around 90% of its fossil fuels, oil, gas and coal, are now imported. Of course, this increased when the UK exited from the European Union. What they really realized was that actually they were importing a large amount of greenhouse gas emissions. Of course, the CO2 is dealt with by the emissions trading system, but methane was not being caught. So they've introduced a regulation, and I'm not going to go through all of the stages, but you can read them here. And there's also a detailed paper on this on our site if you want to know more. One of the most interesting things is that actually the EU ETS will include all greenhouse gas emissions from shipping, which is a large part of fossil fuel trade, from next year. But the actual methane emissions regulation won't fully enter into force with penalties for exceeding the values that the EU is going to come up with in the meantime. It won't come into force fully until 2030. So there's still 5 years, and you can see the stages of the methodology, the equivalence, the intensity, many of which, it has to be said, have yet to be developed by the EU. You can see that on this slide. So let's move to the next slide. And measurement, reporting and verification of methane emissions is extremely complex. So I've repeated in the top part of the slide the various elements that have to be dealt with along the supply chain, and each one of them requires a certain amount of focus on exactly how much methane is escaping from that process, or if not escaping, actually being released. And the more complex the supply chain, the more complicated it will be in order to work out exactly what is happening. I think the main messages, no, whoa, thank you. The main messages from this slide are, when you read generalizations, they are really not at all useful. Every source and every supply chain has different characteristics. So my current research focuses on liquefied natural gas trade, exports and imports, and you have countries such as the United States, which have extremely complex supply chains, and then countries like Qatar, which have relatively simple supply chains. So you have to really look at this in a very detailed and complex way. In addition, comparisons between countries and fuels are very difficult unless you have detailed measurement reporting and verification. So you may read in some press reports that studies have found that coal emissions are not as important as emissions from liquefied natural gas. The problem is that that can be true and that can be false, depending on the details of the different supply chains. The big change in the past 5 years has come from estimating to measuring emissions. And this originated from work in the United States, where the Environmental Protection Agency and other agencies had been publishing estimates of methane emissions from oil and gas. But when particularly academics and NGOs began to measure emissions, they discovered that actually the emissions were much larger than those estimates suggested. And so that is the big change towards accurate detection, transparent reporting, and technical verification. So my last slide focuses on detection methods, which have increased and improved enormously. So from the left, you have people standing on a truck with a handheld camera, and you move through a laboratory and then towards aircraft overflights, which are particularly important, particularly where satellites cannot detect emissions, which is over water, snow covering, and in the tropics. Having said that, the biggest, if you like, transformation of detection has been through satellites, because if you have a satellite and you have overflights which are regular, then you avoid at least you don't avoid it, but you can get readings without having to be physically present on the ground, which in some countries and regions is either not allowed or is impractical. So the most recent satellites, particularly GHGSat, which you see at the top on the right, have got much bigger detection limits and much over a very decent sized coverage. But more to the point, that data will be publicly available as opposed to having to be paid for or not available at all. So the key thing really is that detection is improving with new satellites and with agreements that we need to find out what methane emissions are. Unfortunately, forcing governments and companies to act on even identified emissions is not straightforward. And just to give you an idea, the IMEO, International Methane Emissions Organization, reported that last year it identified 1,500 major emissions from oil and gas, which it reported to the governments of the countries concerned. It had 15 responses, of which less than 10 were actually acted on. So we have a long way to go in relation to emissions from oil and gas and coal. We have made a start. We are getting a lot more action, but so far we haven't had the kind of success that perhaps 5 years ago we'd hoped for. So thank you very much, and I've put my email address on the final slide, and you can access all of our publications from our website there. Thanks a lot.
Well, thank you very much, Professor Stern. And once we get done with the questions, maybe you could, if you can, just put the website into the chat for people that might be helpful. I'm not seeing any questions that have been typed into the chat box or into the question and answer tab. So folks, you can go ahead and type a question in if you have one. Meanwhile, maybe we can start off with just a general question. You told us a little bit, well, at the end, you kind of tempered our hopes for how much progress has been made, but the government and corporate initiatives that you brought up, could you tell us maybe in some specific terms how much progress these initiatives have made in reducing methane emissions so far?
So it's easy to be, if you like, cynical about this. The global methane pledge, which is not just energy, it's to reduce global methane emissions by 30% across 160 countries through all of the sources. We don't really know what's happened since that was signed. It's easy to say, oh, nothing's happened. Probably a lot has happened, but we don't know. Likewise, when we look at the specific ones that I put in that slide, again, some of them have been reported, oh, look, this group has reduced methane emissions from this percentage to that percentage, to which the question is, yeah, great, but actually, which companies have done this and which haven't?
Right.
Now, again, I'm very hesitant. A lot of NGO and academic publications kind of dismiss all this stuff as greenwashing, and I think that's a mistake. Partly, we have got to rely on these guys to reduce emissions because they own the assets, they have the balance sheets, and for them, it's a commercial decision as well.
Right.
They can reduce considerably, and there's every sign that they actually are doing that. And that's one reason I'm constantly being asked, oh, will President Trump basically trash all the regulations in the US? And my answer is, well, he may do that, but I think a lot of the big companies are far enough along to realize, hey, look, this is a good idea anyway.
Yeah.
And it's actually not going to
Wonderful.
cost us very much.
Yeah.
Yeah.
Well,
So I don't think there's a reason to despair. What I am disappointed about is the lack of transparency in actually, yeah, you signed on to this several years ago. What have you done since then? What's been the difference? So that is something that we really need to understand as we move forward.
and see where the levers are. Yeah, thank you for that. There's just one more question. I don't know if it's a quick answer, but we're a little bit behind on time, so I'll just pitch it out there. Maybe it is a quick answer. Is there another source to detect methane emissions other than satellites?
Yep, there are, well, essentially satellites are what's called the top-down measures from the stratosphere. On that slide I showed you, there's a lot of bottom-up methods. In other words, you look at the site and you can see emissions escaping from the assets on the site. The problem is that doesn't capture, or it may not capture, all of the emissions that are further up in the stratosphere. And of course, these are very complex assets over very large amounts of territory.
Yeah, thank you for that. Very good. Well, we'll stop while we were still wishing there was time for more and move on to our third speaker, who is Dr. Jonathan Buonocore. He holds an SCD Doctor of Science and is an assistant professor in environmental health at the Boston University School of Public Health. His research interests lie in evaluating the impacts, benefits, and trade-offs of technology and policy choices in energy, transportation, agricultural practices, and climate change mitigation and adaptation. Dr. Buonocore, I'm passing the microphone over to you.
Great, thank you. Thanks for having me here. Yeah, so I'm going to talk a little bit about, I guess both of the previous talks have talked a bit about the climate impacts directly related to the methane emissions. So I'm going to talk some about the different health impacts related to different pieces of the natural gas system. So could I get the next slide? There we go. Okay, so to kind of ground things, I'd like to think about our state of knowledge using this kind of flow chart here. That's the risk assessment processes that get used at least by the US EPA, if not some other environmental agencies, and definitely in academic world as well. Where it starts just by asking this very simple question of hazard identification, whether there's any problems caused by the pollutant, or safety issue related to anything. There's a dose response assessment that basically asks, like, does the amount of harm change with the level of exposure? In parallel with that, there's this exposure assessment thing that basically asks how much people are exposed to of this stressor, of this pollutant, whatever it is. And when are they exposed? How many people? And like, are there any specific windows during which they're exposed? Like infants, other vulnerable populations, and that kind of thing. And then at the very end of this is this risk characterization step, which just asks just how big of a deal is this anyway? What are the extra risks of something bad happening? So next slide, please. There's a bunch of animations here. So the way that I often do this is I kind of arrange these in this placard that looks, at least in the US, you will see these on the back of like tanker trucks to kind of give safety information about whatever the truck is carrying. So the first one here again asks, like, is there something going on that might be harmful? The second one, next animation. Just asking if someone has been exposed. The exposure assessment asks how many people are exposed to it. And then the last one, how big of a deal is this really? So next slide, keep that in mind. So I had too many animations here. One more. So this is the supply chain of natural gas and oil. So it starts out on the left. There's the previous speaker mentioned the complex supply chain. This is what the supply chain looks like. There's this whole step around exploring for oil and gas, designing, construction, and producing and building the actual wells. Everything gets processed. There's this process to get out water, separate oil from gas, separate sulfur out, and get through these other impurities. From there, it can generally go to two different places. The first is that some of the gas will get kind of separated to produce propane, ethane, which is a big plastics feedstock, and then other whatever else is found in the natural gas liquids. The natural gas part of this, the methane part, and some of the ethane often gets enters then the natural gas supply chain, or it gets processed. It enters this big network of pipelines. Goes through a whole variety of processes depending on where exactly in the supply chain you are. It could go into underground gas storage, where we've, at least in the US, we have reused old oil wells to store gas, basically seasonally. Go through refining and that kind of thing, and then eventually get to oftentimes a local gas company, where it then gets distributed to buildings, residential, commercial businesses, and in some cases it gets used for vehicle fuel. Other end users include industry and manufacturing. It gets used a lot in the petrochemical industry to produce plastics. Some of it, much of it goes to power plants, and some of it gets exported to go to the European Union, the UK, and other places. And next slide, please. Animation. So this is what we know. There's a hazard basically everywhere, since there's been research showing that benzene, which is a carcinogen, is present in gas. So there's a potential for exposure to carcinogens everywhere on the supply chain. We know a fair amount of what people are being exposed to some of these pieces of infrastructure, but not all of them. And only in a few places do we really know kind of how big of a deal this exposure really is. So for the rest of this, I'm going to focus in on a couple little case studies looking at different pieces of the supply chain. So next slide, please. So this is oil and gas production in the US. You'll probably notice that there's a lot of it. And you might be asking, naturally, how big of a deal is it? So next slide, please. So to do that, this is a kind of ongoing collaboration between myself and a research group at the University of North Carolina. We run through a health impact assessment framework to basically model the effect that the emissions of oil and gas different places on the oil and gas supply chain have on air quality, and then I run it through a health impact assessment model to figure out the health impacts. So this is the some results from those atmospheric modeling runs showing the air pollution impact of just oil and gas production. So this is not power plants, this is not industry, this is not buildings. This is just things going on at the extraction site, where you've got wells, you have pumps, you do have flares, and a lot of engines to power everything on site, including provide power to the wells themselves. And one thing you'll notice is that there's a lot of air pollution in the areas where there's a lot of oil and gas production, probably no surprise there. But NO2 on the lower right tends to kind of cluster in areas where there's a lot of oil and gas production. So you can see Western Pennsylvania and West Virginia, Texas, Oklahoma, and Kansas in the middle of the country with a lot of NO2. Ozone on the upper right has a lot of, it's more of a regional pollutant, which is no surprise given the chemistry and the transport behavior of ozone. But you have a much larger plume throughout the country. And then PM 2.5 is somewhere in between. And the numbers here, the 634 exceedances, these are, and the 29 daily exceedances, these are the contribution of this sector to our national ambient air quality standards violations. So next slide, please. So running this through a health impact assessment model that has underlying it US population by census tract, county level mortality and morbidity rates for about 12 different outcomes, and then concentration response functions relating changes in air pollution to changes in these different outcomes. Run these air pollution results through all that, and we get a total health impact of oil and gas production of about 7,500 deaths and about 410,000 asthma exacerbations and about 2,200 newly diagnosed children with asthma. And again, largely clustered in areas where there's a lot of oil and gas production, but you have a lot of impact in areas where there's no production at all. So cities like Chicago in the state of Illinois, which is nowhere near any oil and gas production, is actually the most impacted area. And you see impacts in like Miami, Orlando, Florida, and New York City, and here in Boston, which is pretty far away from a lot of oil and gas production. So it is a very regional pollutant and a regional health impact. Next slide. Okay, so this just puts it in number terms. There's a methodology that the EPA and others use to put dollar values on health impacts. And it ends up being about 77 billion with a B US dollars. Largely the deaths are driving that, but there are impacts of like respiratory hospitalizations and asthma exacerbations and all these other impacts. Next slide. So going to the other end of the supply chain, looking at what's going on in your kitchen, your stove emits air pollution. It emits benzene, which again is a carcinogen. It emits a lot of other volatile organic compounds. It emits NO2, which is a big respiratory irritant, and it emits methane, since the burning is not complete and many gas stoves leak. So next slide. So I was part of a study that did basically sampled unburned gas from stoves. So you can see Boston here. The sample locations are in that bullseye, and the different colors here designate different utility companies. And we have the pipelines on the map as well. So there's kind of a mix of different homes, different utility companies, and different pipelines that are getting the gas. Next slide. And this organic chemistry textbook looking table is what happened when we took that took that gas and sent it to a lab to be analyzed. This is the EPA TO15 protocol for volatile organic compound sampling. And we got a lot of methane and ethane as expected, but we got a whole lot of other compounds, including, I think there's some animations here if you could cycle through those. Benzene, toluene, and heptane, all of which are carcinogens, xylene, ethylbenzene, trimethylbenzene, and all kinds of other things, which most of these are hazardous air pollutants, definitely respiratory irritants, and some of them are carcinogenic as well. Next slide. Yeah, there's the animation. So those are the ones that I'm the most worried about, at least. Next slide. So Go back one. Okay, so this is the concentration of odorants. So gas smells bad because we intentionally add sulfur compounds to it. These sulfur compounds aren't terribly well tested, but they are respiratory irritants, which is why they're unpleasant. There are also some rat studies showing some neurological effects of exposure to these. And this is the concentration of odorants and gas in a few different cities around North America. That tert butyl mercaptan was the highest, but you can see a lot of others in a lot of other locations. Next slide. All right, this is going back to benzene, again, looking across North America. The study in Boston, surprisingly, we had the lowest concentration of benzene. Other cities have a lot more benzene in them, Toronto, in Canada, Indianapolis, San Diego, all the way up through the highest levels of benzene were in Vancouver in British Columbia, Canada, and in Los Angeles in California, and Calgary in Alberta. Next slide. So just again, that's two little case studies from the other end of this, but again, we've shown that there's benzene across the life cycle of gas, and a lot of hazards across the supply chain. So sort of a lot of work to do to really understand the full kind of health impacts of this industry, but this hopefully gives a picture of two of the different hazards. That should be the end.
Thank you very much for sharing your presentation with us. It really helped me to see the visual of that supply chain schematic. So even though the animations made it challenging when you weren't pushing the button, it was helpful for me to see them. If I don't see any questions posted in the chat, so we do have a couple more minutes if anybody wants to quickly post one there. I guess, I mean, I have one question for you, Dr. Buonocore. Who needs to know what you shared with us today in order for us to see some meaningful commitment to progress, to change? I think as a research scientist myself, there are many problems that I work on where I'm like, we have all the knowledge we need in order to solve this problem. We just don't have the political will, in other words, the ear, to change it. And you need that. I mean, we also need collaboration between the sectors. So there's those three things that are needed. What would you say from what you shared with us? I mean, who needs to know this? Where's the blocking point?
Yeah, that's a good question. It definitely, varies depending on where you are, but I think there's a big difference between knowledge and sort of pressure. I mean, if you think about it and dig back in the research, we've known about climate change since I think it was like 1856 or something that Eunice Foote discovered that the greenhouse gas effect was a thing. And we've known about it for 150 years and still have done very little. And I think it's only when knowledge turned into political pressure that people actually started taking action here. Yeah, so I'm not sure who needs to know, but I think knowledge is not the barrier. I think in order to act, people need to be pushed into acting.
Yeah. Okay. Well, I guess, that's how it is for certainly a lot of things. Well, I really appreciate all three of you bringing your perspective to the table today and sharing with us. And if I'm correct, we've answered all the questions. Thanks, Lord Trees, for typing your answers into the Q&A box. I think we've answered them all. And with that, I will go ahead then and thank you all and turn it back to Georgina and Frida and CABI to close us off.
Yes, thank you everybody for joining us today, and thank you to our three speakers coming from very different angles there. Frida and I do work on the One Health Knowledge Bank, so we're very much hoping that people can take things from each of these speakers and look at it again, more research and see how we can approach this problem from a One Health angle. Anything you'd like to add, Frida?
Not much, just thank you all for joining. Yeah, I've learned a lot today, and I really appreciate the answers that were given both verbally and typing in the Q&A. So thank you all for joining. And yeah, as I'll echo what you said, that would be great to see. I think one good thing about these discussions is we're hoping that it sparks a thought for people to think about a way to have a One Health approach. You've heard from 3 different perspectives, as we said before, and hopefully we can be inspired to think about how we can work in different disciplines together to look at this issue. Thank you all, and I hope you have a great rest of your day. And thank you so much, Lisa, for moderating. It was wonderful.
Yeah, thanks a lot.
And thank you all for joining. Our speakers have been excellent.
Yep. Just encourage you all to take a look at the CABI website and see what's there. There's a lot of open access information. Our key points are that we're looking at integrated health approaches. So the animal health, the human health, and as well as the ecosystem in which they sit and how that interfaces. Why would you integrate an approach? Well, you would integrate it because you're going to get an extra benefit. So there's going to be an improved health outcome or a cost savings or maybe an ecosystem resilience. And so that's what we're talking about when we talk about integrated health approaches and One Health. And yeah, so thanks for joining. Nice to meet you all. And we'll check in with you the next time in a month or so when we have another webinar. Thanks a lot. Bye-bye.